All right, welcome back, everybody. The next set of scientific talks, let's kick it off with Emmanuel, who is an associate professor at Princeton, but who's also spending time at EPFL now. Yeah. And he's going to talk to us about universality and limitations of deep learning.
Thank you, and thank you, Seb and Ilya, for the invitation. Can you hear me well? No? Let's see. Hello? Okay, let's see. I think it's not a strong microphone. We'll see. Okay, so this is joint work with Colin Sandon, who's now at MIT. We started this a few years ago now when he was a student at Princeton. We posted the first version on arXiv a few months ago with about half of the story, and hopefully that's the complete story here. We'll post the paper hopefully very soon. Okay, so deep learning has been very successful in image classification, and not just in images that look like that, meaning classical natural images, but also more complex settings, medical images or games. So the question here is, how far can deep learning go? Can it learn any function which is efficiently learnable, or does it have any limitations? And a good starting point to investigate questions like that are this kind of function, where on the first class you have images that look like this, and on the second class these are the images. So there's nothing really in the pattern of these images. The only difference is that there's an odd number of points here, and here an even number of points. So that's simply the parity function. And this was long known to be a difficult function for, in fact, the perceptron. The book of perceptrons by Minsky and Papert spend a lot of time on this case and on the issues that the perceptron has with it. Another case where they spend a lot of time is the one on the cover of the image, which is connectivity. So these are two shapes that are a priori similar. The difference is that this one is connected. There's a single orange shape, and this one has two connected orange shapes that are disconnected among themselves. So a more modern version of this problem would be a model like this, where the function is either a connected graph here, that's an Erdős-Rényi graph, which is above the connectivity threshold, and this is two versions on half the vertices, where there's either no edge between them or there are communities, meaning there's a few edge among them, except that I will break the small cycles, all the cycles of depths of lengths up to root log n. So all these problems have the commonality, I mean those two here and the one here, that there's no clear feature, low complexity feature that you can extract and compose to learn the function. No matter what you try here, there's not a clear pattern that dictates the parity. In fact, the parity is extreme. If you don't see a single of this square, if you don't know if it's active or not, you cannot deduce the parity. So that's the topic. And of course, these were the difficulties that the perceptron had in 1969. And so the simple perceptron with a computational power of 69. And this is what the neural nets look like now. So this was apparently a neural net trained here at Microsoft Research. I got this from Reddit user Matt Files. It's 3 million nodes and 10 million edges. It looks very nice. So it's pretty far from the perceptron and the computational power of the time. And I guess the question is, who can, in this era of deep learning, with the size and the depths, can we learn any function, let's say Boolean to simplify, that can be learned in polytime? Okay, so I want to define this now. What do I mean by deep learning and what do I mean by can learn? So there's quite a few things we know about deep learning, about neural nets. First of all, for the approximation error, any function on n variables that can be implemented in polytime can also be expressed by a neural net of poly size. Okay, so that's just expressibility. But we also know that a poly-size neural net can be learned with a sample complexity which is polynomial. But that, however, is with ERM, and this is a VC bound, and unfortunately ERM is NP-hard. Okay, so the main question in this theoretical computer science framing of the problem is poly-size neural nets with SGD in poly steps. Can this be the ultimate learning paradigm? Using the terminology of the book of Ben David and Shalev Schwartz. In fact, I refer to that book to all the references beyond these claims. So that's the question. Can SGD be the alternative to ERM that makes it efficient and universal? So of course, there's the first issue to worry about is SGD needs an initialization of the weights. And because of the first point here, because any neural net of size polynomial can express any function that we care about, then we could always cheat and preset the weights to be, if you are given a specific target function, to compute that specific function, and then in zero-step SGD, we already learned the function. So it doesn't make sense to ask the problem like this, but we can ask the question in two ways. Either you are given a specific target function, like the parity on the entire set, and now you're no longer allowed to have degree of freedom on the initialization, but you want to show that if with a random initialization of your net, you would still learn the function in polystep. Okay, that's the first way to ask the question. Or we will not force ourselves to not restrict ourselves to random initialization. We will leave degree of freedom for that. But now we no longer have a specific target function in mind. We have a set of possible functions. That's the classical statistical learning framework. Or here I will not really work with a set of functions, but with a distribution on functions. So basically, you have a random function that you don't know which one nature has drawn. And now you can choose your initialization the way you want. But you, of course, you can't cheat anymore because you don't know which one. It has to be agnostic to the chosen function. So the second formulation, for example, in the case of parities, could be the following. You're now going to take the parities, so the xi's are plus minus 1. So this is exactly computing the sign of the vector, but you only restrict yourself to a support S, which is uniformly drawn. Okay, so nature does that. You don't know what S is, and you want to learn what S it is. So if you fail at 2 in this framework, for example, of parities, then in particular, if you fail for, no matter how you choose your initialization, you will also fail for a random initialization in particular. And because a function, a model like this one has symmetry, if I have my ID weights on my neural nets, it doesn't matter which function, which parity function has been, was the one selected by nature, as long as it's a typical one. So if you fail at 2, in a case like parities, you will also fail at 1 for a typical parity function. Okay, so in a sense, if you have a negative result for 2, it implies, in case of models like this that have symmetry, it implies a negative result for 1. Okay, so now I still have to tell you what does it mean to learn, can learn. So the setup we will have in this talk is the following. We restrict ourselves to Boolean vectors for the data domain, so black and white images, and binary labels, so 2 classes only. Px is a distribution on the input, and Pf is a distribution on the set of functions from x to y. That's the notation. To simplify notation, also we will assume that the classes are balanced, so roughly the same number of class 1 and class 2. So that's the probability that you put a label 1 when you sample an input and an f independently. And now we can define what learning means, and this is the definition I will use. We call it weak learning. So you can weak learn a distribution, a pair of distribution for the data and the function in t time steps. If when nature picks a random function according to that PF, you can query t times an oracle that uses the f which nature has picked in some way and the data distribution. So for SGD is the usual framework. You see a data point labeled from px and you see a data point sampled from px and a label from the true function f. And after this t time step of training, you will output some estimator f at of t. And your hope is that, this is why it's called weak learning, that the probability that you get the right label with your estimator, this is the right label, on a new fresh sample at time t plus 1 should be better than half. Okay, half plus a constant epsilon. That's omega. And n here is the dimension of the input. It's this n here. Okay, so this, if you fail at that, you fail, for example, at pack learning, which is asking for more. So in a sense, that's perhaps the first non-trivial concept of learning. Like, it's hard to come up with something that is weaker. This is asking for guessing right, so that's the labeling has to be right for a typical f. That's like expectation over f, as opposed to for all f in your support. Okay, so the neural nets that we will work with are pretty generic ones. So weighted directed graph with a collection of special input vertices at the roots, n plus 1 because there's n input and the constant, and then it's no particular restriction, directed acyclic with weights. And on the black vertices, you have some non-linearity that could be, let's say, a sigmoid. Or I will specify if we need something particular. Okay, is there anything about the setup? So, okay, so the results, I'll start with a negative result. Gradient descent cannot learn efficiently function distributions having low cross predictability. So CP stands for cross predictability, and this is the definition. It depends on the two parameters of our problem, the input, the distribution on the data and on the functions. And it's something very simple. It's simply the correlation between two random functions that are sampled under PF, the expected correlation. Okay? So, for example, if you have a prior PF which is very good, like it's very spiked around a specific function, so if you essentially knew in advance what the function was, then the cross predictability would be 1 because f and f prime would be the same with high probability. So in the extreme where your PF is deterministic, is a delta, then the largest value for CP is 1. If you have completely random functions, then your cross predictability would be 2 to the minus n if you have completely joint function. And the other case which is interesting is that if you have the parity functions that we had in the second slide, then this will have a cross predictability that is also 2 to the minus n, like random functions. So these are all very classic measures, and this is the first notion that comes. So what does it mean to say low CP? It means that the decay is going to be faster than any polynomial. So n to the minus that's what we need for the cross predictability. So if you have this, if your PXPF have this property of having a very weak correlation typically, then you cannot learn, and cannot learn means the following, that if you have any polynomial size neural network, any initialization, doesn't matter what it is, you train it with poly time steps, you have a poly learning rate. So that means in theory the learning rate will even be decaying, but if you wanted to play with large learning rate, it could not be larger than polynomial numbers. Poly range and poly noise, that's the range of values for the weights and the noise that you add on those weights. So in a sense, that's the SNR, the precision versus magnitude of the weights. Both have to be polynomial. And if you have this, if you have all this restriction together, then you will not be able to learn under this low cross spread. Yes?
When you need poly noise, where does the noise come in?
Oh, you add on your gradients, you add noise. So when you compute your expected gradient, you add some noise, and you need to add that noise. If you don't add that noise, this result fails. So this poly noise means that you need to at least have a noise which is polynomial. If you have a...
So just to the directions there. The poly size NN is its most poly size.
Yeah.
Initialization doesn't matter. Poly steps is its most poly size.
It's all at most except the last one. Yeah. They're all at most except the last one. I mean, you
need at least.
Yeah, you wouldn't want a result that says. I mean, it would not make sense to have the other way around. But it's true that I should specify. You need at least a poly noise. If you have if you have zero noise, or if you have exponentially low noise, so for exponentially low, you can still do it with parities, for example, because parities have an exponentially low cross spread. But in general, if your cross spread is not necessarily exponentially low, but it's just like this, then you would need a poly noise.
So the noise is unbiased?
What do you mean by zero mean? Yeah, zero mean. That's the variance of the noise. Yeah.
And what is poly range?
Poly rate is the learning rate that when you multiply your gradient, has to be polynomial. Oh, the range. The range is the weights. They take value in an interval minus AA. And if you are below that interval minus AA, you flatten it to, you keep it there. It's like your overall flow range. Like you wouldn't. So this could be large, n to the 1,000, but it couldn't be exponential. Yeah. So these conditions, yeah.
So it seems that with polynomial number of steps and polynomial rate, you'll not be able to get to a range that's bigger than polynomial anyway. So am I missing something here? Or
No, because you're even at the initialization, you can choose what you want.
Okay. But if initialize,
right, then you can remove. If you do plus minus one in the plus minus one rate, yeah, right. So I can discuss perhaps later on at the end that in fact these are necessary to some extent. If you break any of these conditions, if you remove the range or the noise or the poly rate, we no longer have a result like that, and And for some reason, so I have to say a few things about.
You say necessary, they're necessary for the result or necessary?
No, not just for our proof to work. We believe, we don't have counterexample, we believe they're necessary. Actually, yeah, we have, okay, I'll tell you more at the end.
Okay.
I think they are in fact all necessary. And I think we could potentially find counterexample for each, for removing each. So let me say a few words about papers here that are important. The first one is that this is pretty similar to the statistical dimension. In fact, it's reverse proportional to the statistical dimension. The difference between the SQ framework and this framework, well, of course, GD is a special case of a statistical query. If you're not familiar with statistical query, bear with me or skip this. It's very similar, except the three differences are, A, we look about typical functions, not a class of functions, and we want to do well for any function in that set. So there's the typicality on the function. B, we do weak learning. We just want to beat half as opposed to getting a probability of success, which is 1. And C, we have statistical noise instead of adversarial noise. But this, the third one is the least meaningful differences. The first two are a bit more important. So there's a student who came this summer at EPFL, and we're writing a note about the difference between the SQ framework and this framework of the weak learning here, and why this is an average case version. Also, another important paper, and I'll take the question, is there's a paper by Shalai, Schwartz, Shamir, and Shama that don't exactly establish a negative result for learning, but they show that the gradient in the case of parities concentrates, and this gives strong evidence that in fact you cannot learn parities. Yes?
What is the gradient? What is the objective in which you're using it?
Oh, the loss function?
Yeah. Is it? Yeah.
Yeah, so it's any loss function that is allow you to define a gradient.
Okay.
That has a smooth or even like a gradient which is well defined.
But you're looking at ERM setting.
Right. Okay, so the corollary of this is the following, is that gradient descent cannot efficiently, can learn efficiently monomials of degree k. So monomials are, so x1 times x2 times x3, and you have k term. So it can learn such functions if and only if, so it's a characterization. So learning efficiently is under this hypothesis. K is finite. So you can only learn finite degree monomials. So this is in analogy with what we expect for, let's say, this problem of connectivity that I gave you with the Herder-Schwenny and the stochastic block model. If you break all those cycles that are non-constant up to root log n, then typically we expect that you cannot distinguish between the two models, because in fact this is not going to be calling on, this is going to call on polynomials of higher degree than constant. Okay, so that's the story for gradient descent, and this is of course for the population gradient. So for long, what we tried to do was to obtain the same result for SGD instead of GD. And we kept bumping into issues with the fact that we couldn't get as a clean set of assumptions, just polynomial things. We had to add more constraints and more bounds and more restrictions. We had a result that if you only change a few weights per time step, for example, for coordinate descent, then we get the same result. Coordinate descent cannot learn under low CP, but we couldn't get the same result for SGD. And eventually we found out why we couldn't get the same result for SGD, and it's simply because we had the statement wrong. SGD can learn, in fact, efficiently any efficiently learnable distribution. So you don't have this issue with SGD that you have with GD. So essentially SGD is in fact universal. And to clarify, so efficiently learnable distribution means any PXPF that can be learned by some algorithm in polytime with polysamples.
What do you mean by SGD here? SGD.
Yeah, you mean adding noise, right? GD plus noise.
No, SGD.
No, but on what I'm a bit confused, but on what architecture? SGD on what? What are you doing? SGD?
Any neural net that has polysize, any architecture.
But something is trying to quantifiers here. I mean, obviously I cannot pick any, it's not the case that for any poly-sized neural net, SGD will learn.
No, there exist. of course, it's a positive result. So there exists a poly-size neural net which is of polynomial size. There exists a polytime initialization, so that is agnostic to the function and doesn't use the data. That takes polytime to be initialized. And such that if you run SGD with poly steps, with poly rate, and with poly range, and despite the fact that you add poly noise on top to the gradients, now it's stochastic gradient descent, so it's not expectation, but it's a random gradient, then you will learn the function weakly learn in the way that it's defined. So that seems surprising because SGD, in a sense, is the version that we cannot implement when we cannot implement gradient because we don't have the full access to the population. But it turns out that I'll try to give a little bit of insight that having this gradient, which has potentially larger movement because it's not averaged over all the data, give you some extra freedom, and that allows us, in fact, to learn any distribution.
So I'm confused. So SGD, so gradient descent plus noise in the population likelihood does not qualify as SGD?
No. So there is either you do gradient descent, right, of your loss.
Yeah.
Let's say this is your estimator. This is the true label, and you do this is your expected gradient. That's for a GD, and then you add noise here.
Sure.
The adding noise here is just because we cannot work with infinite precision. So the adding noise is a way to say that we will have some precision in how much we can record our data.
So I guess if I do SGD,
That's GD, yeah. SGD is just you have this random sample.
but isn't that unbiased? I mean, so what is not unbiased? I guess the subset of the is not an unbiased like.
Yeah, it is unbiased, but it has much more randomness, right? In one shot.
Would the resulting have much bigger variance?
Yeah, that's what we like about SGD. The fact that it has bigger variance makes it that in cases that are hard cases, like parities, it has more movements than this, where this is not going to be correlated too much with the parity function. So this is going to be what is useful. Yes?
So we're probably missing something because parities are learnable by a polytime algorithm.
Right, Gaussian elimination.
Right. But so what are we missing here?
SGD.
No. So you're saying that SGD can learn parities?
Yeah.
Okay, make noise.
Okay, that would.
No, even with poly noise and poly precision.
But it can't. I mean, we know that you cannot learn parities with poly.
No. What you're missing is two things. First of all, you're thinking of learning parities with noise, which is a different model, where you have noise on the label.
Right. So here it's noise on the.
Here is noise on the gradient.
Gradient.
It's about the precision of your implementation.
But you're saying you can learn parities instead of Gaussian elimination. You can learn parities by SGD on a polysize network.
Right. That's a surprise because SQ algorithm cannot do it.
Right. It's very surprising.
Right. So also two things. A, the learning party with noise is noise on the labels.
Right.
B, if you add polynomial, the noise has to be at most here. It has to be at most polynomial now because it's a positive result.
Right.
If you add that, these are different noise models. But if you just do a hand wavy analogy, and if you add noise which is that small, it's still a pretty small noise, then you would still be able to learn parities in the model of LWE with Gaussian elimination. Gaussian elimination is still robust to that amount of noise. However, SQ algorithm would break down for parities even with that amount of noise. So that's the corollary. So SGD can learn efficiently parities, while the perceptron GD or SQ algorithm cannot. Yeah.
I'm still confused. Just so with your definition of efficiently learnable here, so you're saying by some polytime algorithm?
Right.
But this is a distributional statement. So what is that, right? Because it's against PF. Like typically I think of like a polytime algorithm is on an instance, but here you're saying.
No, a polytime. So did you see the definition for learning? It's this one. Here. So you're given a PX distribution on the data and a PF on the functions. And now you define learning. It's like PAC, except that we ask for a weaker requirement. So it's for that class of PX, that class of PF, you have some algorithm. So think of parities. parity, you have the uniform distribution on the inputs here, and the PF is a random parity function. So that you can do with this quick learning easily, with building a basis, doing a Gaussian elimination, or inverting the system, and then you will get not only half in the case of parities, but you can go all the way up to 1.
Can you say something about the method being learned? Does it actually learn Gauss elimination along the way? Or?
Yeah, you will see. It will probably be disappointing. It's an emulation argument. It's an emulation argument. We will reproduce Gaussian elimination with SGD.
And what do you do, for example, for connectivity? Whether you have
okay, connectivity is a longer story because I haven't given you a class of function. Like for parities, we have an obvious class, and then we know for connectivity, you first have to build a class of function. Just to tell you that, I'll probably burn all my time. So if you want, you can talk afterwards.
So I do have a question.
Yes.
How is it related to theorem 1 related to the result by Mahdi that says that if the S...
Sorry, I can't hear you.
How is that theorem 1?
The negative result?
Theorem 1, the negative result. How is that related to the characterization by Blum and Friend, that you can SQ, if the SQ dimension is Polian, you can basically learn a class by SQ algorithm even only if the SQ dimension is Polian.
Right. So that's what I said. That's what I said before. So with the SQ framework, there's 3 differences. The first one is that you don't care about the typical function f, but you care about the class of function, and you are worst case on that class of function. Okay. Then there is that here we care about weak learning. We just want to beat epsilon.
But they also have there is a characterization that talks about weak learning. So there is a theorem that says if SQ dimension is Polian, then you can weak learn a class by SQ algorithms. I think it goes the other way around as well.
I mean, I can look at the paper. Maybe I don't know this one, but essentially, what is true is that you would also get a negative result for SQ. As I said, this is similar flavor as SQ. Slight different setting, and I'll send you this note if you want to see the differences. Maybe we missed that reference, but the quantitative feeling is the same with SQ or with this. It's not exactly the same setting, the one we knew, but the flavor is the same. If you have a statistical dimension which is exponential, then you're doomed. Likewise here, if you have a cross-predictability which is exponentially low, then you're also doomed.
Yeah, so there is a result by Blum, Kearns, Merrick first, then there is basically, if the SQ is Polian, you can weak learn by SQ algorithm if and only if the SQ dimension is Polian. And
I see. So interestingly, okay, I'll check. Thank you. Interestingly, I met Kearns himself on Thursday. I told him this result, and he said that was amazing. He didn't know about it. So maybe he forgot his own paper. Maybe he forgot his own paper. Yeah. Okay. Other questions? Okay. So I'll tell you a bit about this result. About first the CP, how it emerges, the CP. Okay. So the plan is the following. Oh, time-wise, I have 3 minutes. I guess it's 5 with okay. So. This is a gradient descent with the expected gradient and plus the noise. So that's where the noise is, right? And the subscript h here is a placeholder for f or star. If it's f, it means you're training gradient descent with the true data that uses df, which is the data with the right function f. And if you see star instead of h, then it's the junk data, which takes a random label on the data. So the proof strategy is that we will show that the output of the algorithm after an horizon which is not too large, which is polynomial, when you train on the true data or the junk data, is indistinguishable. That it has a total variation that tends to 0. And then by a total variation bound like this means that the probability that you guess right with the true data, when you run this on the true data, is upper bounded by when you change the model here, when you take the star model, which is junk, which by construction will have a probability of half of guessing right because you train on junk data. And here, of course, you have to put the total variation distance between the measure. So QF is a measure of WF and Q star of W star. Okay, and what's important here is that this is the expected expectation over F because we care about this weak learning, about this typical case. So then the first step here is just a subadditivity argument. We want to argue that the total variation distance when you run these two algorithms on the true and on the fake data, for t time step, this is subadditive. This is less than t times the distance you get in one time step. This is essentially fairly direct. It uses the data processing inequality and the triangular inequality to run an induction. Okay, so then you do pin-square inequality. So we are here between the total variation distance of the QF and Q star. We have Gaussian noise, so we can upper bound it by the root of the KL divergence between the two measures. And with Gaussian noise, this becomes simply the means that are subtracted in L2 norm. Okay, so this is now a bit more intuitive. What we care about the expected gradient under the true data and the junk data. How far can they be to each other? And for parities, of course, you can see how this is going to be an issue, because parities is pretty close to random data. But now we have to make this formal. So here, from here to here, I simply isolate this L2 norm is over all edges of your neural net. So we're just going to pick one specific edge, I call E, and we want to upper bound this L2 norm between df gradient E and gradient under true and junk data. And I just changed the measure. This is a Radon-Nikodym derivative. And if you here do the Cauchy-Schwarz inequality, which is what we want to use eventually, the problem is that if you apply, so this is an inner product between this term and this term. If you do Cauchy-Schwarz, then this guy has actually norm which is simply 1. Its square is simply 1. So you lose all the information about f. So that doesn't get you anywhere. What you would like to do is bring the averageness over f, the typicality over f, over this term here. That would be much better. The problem is that you can't bring EF inside because we have a square here. So it's not a linear operator. So we're just going to create linearity as the classical trick. We're just going to lift things. So we write things instead of a square inner product between those two things here. It becomes a no squared inner product between the tensor 2 of each of these functions. And now I can bring the expectation of f over this term. And now I'm going to use Cauchy-Schwarz. And so putting back the pieces together, here I get the expectation of the gradient square. That's the first term in Cauchy-Schwarz. I unfold the tensor. And here I just write this term, the expectation of this one tensor 2. I write it with, okay, that's just a fancy name replica for saying that we take 2 IID copy of a random variable. So it's just here, this is just doing this. If x1, x2 are IID. Okay, and now you can see that df by dx, this is something which is very simple because it's the true data by the fake data. So they both have the same px for the input. So this is a distribution on x and y on the data and the label. They have the same px that simplify. And one has the true measure on the label, and the other one has always a half. So this quantity here, you can see that it's simply checking, it's going to be either 1 or -1, whether the label is right or wrong. And this is what the cross spread measures. So with some massaging and putting the pieces together, this is exactly the bound. So the bound looks like this. The generalization error, well, actually, here it's written for the success error, not the generalization. So the probability of getting the right label when you train after t time step on the true data, it's upper bounded by half, plus 3 terms, 1 over the noise that you add on the gradients. This GF, which refers to junk flow, it's how much gradient can you accumulate when you run your neural net on junk data. Okay, so you have some neural net with some initialization, could be random. You train it on junk data. This will generate some gradients at each time step with some learning rates. And this is like the intrinsic momentum that pure randomness gives you. And this gives you the first term here. And then the second is the cross spread. You can slightly improve the 1/4 here, but it's not important. So that's where you see what happens. If this junk flow is polynomial, like it is when you put the restriction that I had in the theorem, then if the 1 over sigma cannot fight the cross spread, then you can drive this bound to 0, and then you get something that tends to half. So that's the proof technique. So I don't have time, so I'll skip the emulation argument and stop here.
Any questions?
Yes.
So where exactly will your proof fail if you look at unlearnable function such as the quadratic residuosity modulo number n?
It failed directly because we need to have some function that can learn and to emulate that function.
Your proof, you were just looking at distances between those distributions. You didn't see a particular point where your proof will fail or where you were using the learnability.
Oh no, you talk about the negative result or the positive result?
You cannot learn the quadratic residuosity mod n in polynomial time, otherwise you'll also factor.
Right.
The proof was only for the negative.
Yeah, that's for the negative.
That was for the negative.
It's only for the negative.
Yeah, for the, yeah.
Yeah, sure.
Okay. Let's thank Emmanuel again.
That's for you.
Instead of saying, I'm still in conflict.
Next up, we have Mahdi, who will tell us about demystifying generalization and early stopping in neural networks. Mahdi is an assistant professor at University of Southern California. Take it away. Thanks.
Thanks a lot for the invitation. Thank you for the invitation to be here. Can everybody hear me good? Okay, cool. So before I start, this is joint work with Samet Oymak, who is a colleague at UC Riverside, and our students Zalan and Mingchen. Zalan is actually in the audience. So the motivation, we've heard the story multiple times today. So it's overparameterization without overfitting. Just to recap quickly, we have more parameters than training data. And now the question is, like, we expect something like this to happen because we're overfitting, but everything seems to be perfect. So the challenges are, one has to do with kind of optimization, which is why can neural networks fit despite the non-convexity, and then why can they predict? And so let me just remind you of some of the experiments that kind of demonstrate this, and Peter showed this earlier. So here, one simple experiment is like you have your training labels, and you just corrupt a fraction of those training labels. So you take like a 0, you change it to 8, you do this randomly. And as you change the fraction of the amount of label corruption, the fraction of labels you corrupt, you look at the accuracy. So I'm depicting 3 accuracies here, and it becomes clear why in a moment. So first of all, you see that the train accuracy is perfect. So neural network can fit even with these corruptions. If you look at the test accuracy, it's not great, but it's actually pretty high. It's surprisingly, it's better than random guess. And this is actually what Peter discussed this morning. Why can even overfitting in this model, why can you still get non-trivial test accuracy? And finally, the orange curve I'm demonstrating here is like now I'm measuring accuracy with respect to the ground truth labels. And that obviously should be bad, right? Because, with respect to the ground truth labels, you should not be doing anything nice. So now I'm going to maybe a little bit of a more surprising experiment. I'll just repeat the same experiment, but now stop early, okay? So now things change quite dramatically. So the train accuracy goes consistently down, so it's not good. Because we're not overfitting to the trained data anymore. But what is perhaps more surprising is that if you look at the test accuracy, it's pretty good. And in fact, the train accuracy with respect to the ground truth labels is consistently very high. And in fact, up to a large fraction is exactly 100%. So meaning I only fed the corrupted data in my neural networks. But if I stop early, I actually get the true labels out. Okay, so that is the surprising part. So these are kind of the experiments we want to try to explain a little bit. Okay, so and really what I'm kind of very interested in, we don't necessarily get to this picture yet, but it's really to understand how the train and test accuracies evolve across time as you're iterating via gradient descent. So I'll talk about like kind of 3 related stories. The first one is like optimization, then generalization. If there's time, I'll also talk about why that early stopping really helps here. So the optimization result is pretty straightforward. So I'm just going to focus on a 1 hidden layer model and in a regression setting. So I have d-dimensional features. I pass it for a nonlinearity, k hidden nodes, and then I aggregate. And I'm just looking at a simple regression model. So this is not classification. So I just fit like a least squares model like this. And here is kind of the theorem. I start from a random initialization. We run gradient descent. So the result here is like if the data points are distinct and you use like a smooth activation, let's say the soft plus activation, and your model is over-parameterized in a sense that the size of the training data is less than twice the width of the network, then if you initialize at random, you actually get zero training error with high probability in the sense that your error goes down at a geometric rate. Okay, so that is the result we currently have. We think that we can actually improve this further, but this is not completely said yet, which is like if we also assume that if you aggregate your training, the input training data as rows of a matrix, if this matrix has full column rank, then you could actually do this with training the data less than twice the number of parameters. So there has been a lot of interesting results recently in this space, including some of our own. The difference is that those results usually require the width to grow polynomially with n, and they also have this requirement on some sort of minimum eigenvalue of some matrix, right? But here is the constant is 2, right? So there is no dependence on that quantity. So that is this. I have to say that this you should not view it as a necessarily a good result. This is more of an existential result. And I think a lot of people already mentioned this. This is just saying, okay, gradient descent can fit everything, but it doesn't mean that this is the right learning regime. So this is very much in the lazy training regime in some sense. But the point is that you can take this argument to the very limit of training data being on the order of number of parameters if you want.
Is it too important in any way?
Yeah, in this result, I don't know in reality what the constant should be. For our result, it's very much important.
But isn't this rely on the fact that the data are separable?
No.
They're too long.
So it's this one, again, this one is still, we almost have a proof. This one, there's a caveat, that's why there's a star. But we think if the data points are distinct, this is full rank, this whole. So the one that I'm, this one, that you should look at that for now.
Yeah. In terms of existence, isn't k larger than n trivial or like it?
Yeah, okay. Yeah, but the point is like we were just looking at gradient descent. Again, all of the results are already in the n to the 4 kind of regime.
Yeah, but I'm even surprised by the n over 2. I mean, what's trivial is k bigger than n. Like 1 times n.
Yeah. Did I do last? Yeah, this is correct.
Is it? Yeah.
So this is worse though, right? Like because
k larger than n or n over 2 or 2n?
Oh, maybe did I put the 2?
Like 2n I back.
Yeah, sorry, it's 2n. Yeah. So I think I put the 2 on the wrong side. Yeah.
What is
exactly.
k?
K is the width of the network.
So the number of parameters is more than k, right?
Yeah.
K times t plus.
Yeah. So that's kind of this. Really, what we're hoping is like the amount of over-parameterization. Hopefully, I put the 2 correctly here. Oh, this should also be on the wrong side. But we believe you can show if the parameter is bigger than twice the size of the training data. You over-parameterize by a factor of 2, then you're fine. But this result still has an asterisk. So, yeah. So that's the kind of idea. So again, but this is very much doesn't say that you just find a global optimal, whether it's useful or not. We have to still see. So what about generalization? And so we have some theory for generalization. You can tell me if this is useful or not. But basically, in this case, we look at a classification model. So it's a multi-class classification model. So I'm going to assume the output dimension is in capital K. So the labels are 1 hot encoded. So that's the setting. But I'm still going to fit this using a least squares model. So I'll basically, the input dimension is D, hidden noise is little k, and then the output is capital K. And I just fit a least squares model. So obviously, I can aggregate all of my data points and just build a very large nonlinear least squares problem. That's what we do. And we just run gradient descent on this. And I just want to point out that gradient descent here takes a very particular form, which is kind of the Jacobian of this nonlinear mapping times like the residual. Okay. Oh, and I should have mentioned that in this result, we fixed the output layer, and we just train over the input layer. So here, to do the actual final prediction, we just look at the closest class to our model, right? So we pass it for a softmax, pick the maximum, right? That's how we do classification and with this least squares setting. So we're not using cost entropy. The key observation that we think might help explain some aspects of generalization is that if you look at this Jacobian of neural networks, they seem to have some sort of particular eigenstructure. And here we're looking at part of basically the CFAR10. We look at only free classes. We actually now have results on a full CFAR10, but it's not completely ready, so that's why I'm not showing it now. But basically, if you look at the histogram of this Jacobian, the eigenvalues of the Jacobian, whether at initialization or after a lot of training, what you observe is that there's a lot of there's a lot of small singular values, and there's a few that really pop out. So there are a few large eigenvalues, and the rest are pretty small. So it kind of seems like the Jacobian has some form of low rank structure. Again, not exactly low rank, just in the sense that there's some eigenvalues that are really large, the rest are pretty small. Okay, so this motivates us to think about this Jacobian structure in our results. So as a reminder, gradient is like Jacobian times this residual. So, and given that it has this particular structure, this kind of motivates the following definitions, where we basically pick a cutoff level for our eigenvalues. Things above some cutoff level, we call it like the information space. The rest is kind of nuisance or noise space. So that's kind of what. But here alpha is a free parameter where our results hold for any alpha, and then you can pick the right one to give a good result. So here is kind of our theory is we fix the output layer like this. We initialize W0 at random. So the J we pick is kind of the J at initialization. This is related to this kernel regime. Then our result says that if you pick alpha proportional to square root of n, and well, you can think of alpha bar like a constant, if the width of the network is proportional to 1 over alpha bar to the power 8, then the misclassification error you get is less than how correlated the labels are with the small eigenvectors of this Jacobian over square root of n. And then there is other terms which would be negligible. So essentially, this result is saying like if the labels are correlated with the small eigendirections, then they're small. So again, the kind of story we want to show is really like in the large eigendirections, learning is kind of fast. You also train very quickly, and you generalize easily. But if you move toward like the small eigendirections, you might pick up some nuisance or noise or things of that sort. These results also, so roughly the story is that if your data set is structured in the sense of the Jacobian having this particular structure, even with constant width neural networks, you can actually generalize and so on. So I should mention that this, in a special case of capital K, the number of classes being 1, and if you pick alpha very small, it recovers a result by Sanjeevaro and his group, except that we require this width. Basically, those results say that if the network width is bigger than n to the 8, then your misclassification error is no worse than a kernel problem using the kernel at initialization. And so we can recover that result as a special case with n to the 4. But here the key idea is that actually because this Jacobian is low rank or approximately low rank, you don't need to fix the entire spectrum, but only like really the top portions are enough. And you can get away with much smaller width. So that's kind of the intuition. Our results also hold if you start from a deterministic initialization instead of a random one. The only difference here is that it's not the label that matters, but the initial residual. So this one is perhaps useful because sometimes you don't initialize at random. So maybe you pre-train your network using some other model, and then you apply this. So it could potentially apply in this transfer learning models. And the second reason, maybe this is interesting, I think a lot of speakers already touched on this, and the Nati perhaps will do also, is that this, if you have it for a fixed kind of initialization, this could apply for different iterations. So our results would say, okay, even if the initial labels are not correlated, if at some future point it becomes better, if the correlation becomes better, your generalization error might improve. So the rough picture is like, maybe you don't use the kernel, which is like it's Jacobian transpose at initialization, but you can think of this as kind of a kernel learning problem where the kernel keeps getting updated. So if at some point this kernel becomes more suited to your data, then our generalization result would be better. Of course, we're not proving that kernel becomes better. That's kind of the open part. But it kind of gets to this idea of adaptation, which is like, just the kernel at initialization may not be good enough, this kind of lazy training idea, and maybe this kernel is becoming better. So that's kind of related. We were not proving that this kernel becomes better, but if it does, our results would apply. So just to show a clear example of what our results kind of say, let's assume we have like a mixture of Gaussian model. We have k classes. Each class contains maybe c clusters. So we have mixtures of Gaussians. So in this case, you can kind of specify everything I said. So for example, you can check that the Jacobian is approximately of rank k squared times c. And if the network is this wide, you get it kind of like a generalization error that looks like this, the misclassification error. And as you can see, the number of parameters of your network does not appear here, right? It only depends on the number of classes and the number of clusters per class over n. Doesn't matter how wide you make things, right? So that's kind of the result. And I just want to mention, even in this special case, you can see why going to low-rank structures are important. Because as you let the noise go to 0, if you look at the previous results, the width that is required kind of blows up. Because they depend on the minimum eigenvalue of this kind of Jacobian stuff. So let me also demonstrate that why maybe this is not too far off even for deep neural networks, that something like this might be true. So here, so we're again looking at a free class, like free classes in CFAR10. And so the top eigenvectors we look at is like the top 50. What here I'm demonstrating is like the residual. So that's the residual is like green. The residual projected in this top 50 dimensions of the Jacobian, and then the remaining part. You can see that actually residual on the top eigenvectors goes down fairly quickly. On the other directions, it goes down very slowly. And so this is consistent with the picture we want, which is like learning is fast, both in terms of train and test on these top directions, but it's slow on the remaining. And this is kind of the quantity that appeared in our results. How correlated is y with respect to the top eigenvectors or with respect to the small ones. So this is what I want to point out is like as we iterate, so at the beginning the correlation is high, but if you iterate, the correlation becomes better, which goes back to this adaptation idea, which is the labels become much more correlated after training with the top eigenvectors of the Jacobian. So this seems to be somewhat consistent. If you use Adam instead of like an SGD, somehow this adaptation becomes even better, at least in our example. It goes all the way to 99%. But again, this is not something we can explain. We're just saying that, this might be interesting. So these are similar results. If you add label corruption, you can see like this decomposition can help explain why like this dip in a generalization error happens. And finally, just to see that this quantity that appears in our generalization result is somewhat correlated with what you see in terms of test error. So here we're varying the amount of label corruption. This is the quantity that appears in our upper bound, and this is the actual test error. And you can see that they do somewhat grow in tandem with each other. Yes?
Can you just flash the thing with the test set? So that's the test error that's going back up, right?
Yeah.
So you said like our theory is able to explain why it's going back up. Can you just...
So roughly our theory, it gives you like this decomposition that on the top eigenvectors, it goes down quickly. And then on the small ones, I said that sometimes you may pick up noise. If you have label corruption, that's clearly what happens. It goes down, but it goes up again if you iterate. And so now if you add these together, that's what the curve we get. So that's kind of the... So I'll maybe in 2 minutes, I'll just discuss what our early stopping result is. It's still very preliminary, but so it's about this experiment, which is why is it that if I stop early, suddenly I can correct all the corruptions in my training data. And so here we assume like a very simplistic model. So think of it again as kind of a mixture of Gaussian kind of model for the input data. So we assume there are multiple classes, but each class consists of different clusters. So there are overall L clusters and capital K classes. So again, we look at, so now I take my clean data according to this cluster model. I take a row fraction of it, and I just corrupt it in the sense that I replace it with some other arbitrary label. Okay, so that's the kind of setting. This is the corrupted data I have. So again, we fit least squares and we gradient descent, and we just find the closest one to our model. So our result says that as long as the corruption level is less than a constant here, in this case 1/16, and the network is sufficiently overparameterized in terms of the number of total clusters, then if you stop proportional to this quantity, then the closest label to your model is actually the ground truth label. So meaning like I started with like those uncorrupted data, I corrupted a fraction of them, you actually get the true ground truth label. So you perfectly recover the correct labels. So that was our theory for that. And here the key intuition is actually twofold. One is, again, this idea of the Jacobian being low rank. And the second one is that this Jacobian matrix, if you look at the top eigendirections, they're very diffused. And so as a result, if you look at when you're updating using gradient descent, you get Jacobian times the residual. So what happens is you can think of the residual as kind of the residual with respect to the corrupted labels as being residual with respect to the true labels and the corruption. Because I only corrupt a fraction of the labels, this corruption is sparse. And so when I'm hitting the Jacobian with the residual, the true labels, the residual with respect to the true labels falls on the top eigenvalues and goes down quickly to 0, whereas basically the corruption falls on the small eigenvalues, and you can fit it only after many, many iterations, right? In the first few iterations, because it's almost in the null space, you won't even see it. And this is why if you stop early, it's as if you never saw the corruptions, because they're kind of in the null space. So that's kind of roughly the intuition. And so let me conclude there. So I talked about 3 results. One is like, when can you get like global optimality? Maybe some ideas about generalization based on how correlated your labels are with the eigenstructure of the Jacobian. And finally, I discussed this result about early stopping. And so let me stop there.
Questions? So I think I missed some part of the talk. Did you show that neural networks Jacobians have low rank?
No, so that's kind of so we only showed it in this cluster model, right? Oh, so I'm going the wrong way. So it's a concrete example. We don't know why they have exactly low rank. It's all predicated on the fact that they do. The only way we can actually formally show is for this mixture of Gaussian model. You can show that everything checks out. But if it has this eigendrop, we can prove results about it. But numerically, that's what we observe.
I see. And you require this to hold for the entirety of the training, or just?
No. So our results are both basically. If at some point during training this happens, then you're good.
Oh, really?
Yeah. Go ahead.
So, people also curious about the vector of the Hessian matrix of the.
Oh, so I think they're actually pretty closely related. If you look at the eigenstructure of the Hessian, it's actually one term plus Jacobian transpose. So I think actually the Jacobian transpose, I think is the dominant part of the Hessian. So maybe that's why I think they're related. Our results are based on the Jacobian, but I bet like Hessian would be as good.
Okay.
Yeah. Cool. Let's thank Mahdi.
Our final talk of the afternoon is by Nati Srebro. Nati is a professor at TTI Chicago, and he's going to tell us about the geometry of optimization and learning.
Okay, thanks. Thanks for sticking around. So I'm going to, I initially planned on giving a more maybe higher level view about the relationship between optimization and geometry and how that affects, that plays the key role in deep learning. But I saw that actually I think many of you have already heard some version of that talk, and that already also many of these ideas were mentioned before. So I'm going to be trying to mostly talk about some more specific aspects. But since some of you might not remember the talk, what we're going to do first is get it. You remember these old TV shows? At the beginning, there was like last time, and the recap of the last few chapters, and they're really, really fast, and you can't really understand what's going on there. But if you saw it before, then maybe it'll jog your mind. And if you haven't seen it before, I'll be super impressed if you'll be able to understand. But at least it'll be an advertisement, and you can go see the rerun. So the advantage is now all these shows are recorded. And you can easily find reruns of me giving a slower paced, more understandable version of this talk. So you should say that this is joint work with a bunch of people. The part and mostly Jason, Surya, and Daniel, and a bunch of other people. Okay, so. By this point, I don't have to. So this before I don't have to tell you that something is. Initially maybe strange is going on in deep learning, that as we increase the size of the model, we're actually, instead of overfitting, we're actually generalizing better and better and better. And what's going on here, this is surprising for two reasons. One is the complexity is increasing, but we're actually somehow improving generalization. And the second is, even if we just look at a fixed size model, we're getting a very good test error by just minimizing the training objective, but there are actually many other ways of minimizing the training objective. So all of these points here are global minima of the training objective that generalize horribly. Okay? So why is it that the global minima that we find actually generalizes well and the others don't? And Peter already alluded to this several decades ago, in saying, well, what's important is not really the number of units. What's important is some control over their norm or size or magnitude. And in fact, if we put here some measure of norm, then we see that these global minima of the training objectives that have high norm don't generalize well, and maybe this one generalizes well because it has small norm. But this begs the following question. One is, what is this norm? I put here the path norm, but it's not the right one. What is the real measure, the complexity measure we're minimizing here? The second, how is this controlled by the optimization algorithm? Because we didn't tell the optimization algorithm to find us a low norm solution. It's somehow implicitly finding a low norm solution. And in particular, if we change optimization algorithm, we're going to change everything that's happening. We're going to change our complexity. We're going to change what our inductive bias actually is. And we actually can see it. There's a blue algorithm, a red algorithm here. Both find global optima, but one global optima is much better than the other, and tends, in the sense that generalizes better. So again, this is an unfair thing to say that it's better. Both of them are global optima of the optimization objective. The optimization algorithm in both cases did exactly what it's supposed to, but one of them somehow found a better global optima that's better in some mysterious quantity, in particular generalization, that we did not actually tell the optimization algorithm. We can see this in other blue algorithm, red algorithm across the board. Many optimization algorithms that optimize this exact same objective, but some of them return global minima that are better. And I think Leon also alluded that in his talk before, which means that really we're talking about training deep networks. Maybe what's more important is not the model class, but what's more important is how we actually perform this optimization. We change how we perform the optimization. It completely changes what really our learning algorithm is. Okay? So the way we should really understand deep learning is not that we have some model class and we're searching in that model class and finding an optimum, but really what's optimum of the training objective. But it's really what's important is how we're searching in that space. Because roughly speaking, what's going on is that I search in a space using some geometry, and I'm going to find a solution that's maybe close in some sense to this where I started under that geometry. But if I change my geometry, I'm going to find a different global optimum. Okay? So these are two different trajectories of optimization. I'm going to get to different global optima here. Okay? So And in particular, the models we're looking at are highly overparameterized models. So there are tons of global optima. The way you should roughly think of this is the global optima are the oceans. Okay? And we're going to optimize, and we're going to start on some hill, and we will eventually going to find a global optima for our training objective. So we're going to find a point at sea level. But which point? We're not going to go to the middle of the ocean. We're going to go to a beach. And which beach are we going to go to? If we start optimizing here, we're probably going to get is Lake Washington at sea level? I'm not even sure. Okay, we're probably going to get to either Puget Sound or Lake Washington. If we start optimizing in Boston, we're going to get to the Atlantic. And the question is, what happens if we start optimizing in Chicago? Okay, so if you can go down you can optimize from Chicago and go down and get either to the Atlantic or the Gulf of Mexico or to the St. Lawrence. And the thing is that all of these things, where you're going to go is going to depend on which directions your optimization algorithm likes to go to. And the thing is, in very high dimensions, all the places are kind of like Chicago in the sense that you can get lots of places just by changing your geometry. Okay? And so the key here, in order to understand what actually happens in deep learning, we have to understand what are the places these optimization algorithms are going to go to. And that's what's going to give us all the inductive bias. And we'll get back to this a bit later, but an important thing here is I would argue even more so that in fact the model class we're optimizing is so unimportant, it's just all functions. Okay, so we know that with large enough neural nets we can really approximate all functions, and I would roughly argue that we are actually in that regime. We're optimizing over networks, at least we want to try to optimize over networks that are so rich they can capture all functions. So the model class itself is not important at all. What's important is only how we search inside it. So how is in searching inside this model class can really give these biases? And so the simplest example to give is just an underspecified linear regression model. Okay, so there are many optimum for this problem, many W's such as that have zero error here. But if I use gradient descent to optimize it, the W that I'm going to get to is not just going to be any optimum, any global optimum. It's going to be the minimum Euclidean norm global optimum. Okay? So note that I did not specify, the objective function here does not specify the Euclidean norm. Okay, the Euclidean norm is only specified implicitly by the choice of optimization algorithm that I chose to optimize it using gradient descent. Okay? And now we can kind of decouple this. We understand the geometry of the optimization and how the optimization gets us to not just any solution, but a minimum Euclidean norm solution. If the Euclidean norm becomes our inductive bias, if that is a good inductive bias, we'll get good generalization properties. By changing the optimization algorithm, we're going to get to a different solution. So for example, if instead of gradient descent, I optimize with mirror descent with respect to some potential function, or natural gradient with respect to the geometry generated by psi, then at least with the small enough step size, with infinitesimal step sizes, what I'm going to get now is not to the minimum Euclidean norm solution, but the minimum psi solution, whatever psi is. And again, we can see a link here between the geometry of the optimization and what the inductive bias becomes. Now, instead of having a model-based Euclidean norm in terms of learning, my learning actually becomes learning in terms of this potential function. Okay? So this is with the squared loss linear regression. We also see a similar thing with logistic regression. So take logistic regression on separable data. Okay, so if you have separable data, right, linearly separable data, and you train a logistic regression model in it, so it's going to find a way of separating the data, but there are many ways of separating this data. Okay, so if you train your logistic regression model with gradient descent, what you're going to get, the gradient descent is going to converge not to just any separator, but it's going to converge exactly to the hard margin SVM separator, the separator that maximizes the Euclidean margin for the data. And again, our objective function here is just logistic regression. It does not include the hinge loss. This is not part of it. The Euclidean norm is not part of it. Okay, the fact that we're getting a large margin comes from the choice of optimization algorithm. Okay? We change our optimization algorithm, and again, hard margin SVM solution in many cases is a good thing to get to. But if we change our optimization algorithm, instead of we optimize the exact same model, okay, logistic regression, but instead of using gradient descent, using coordinate descent, also a perfectly reasonable optimization algorithm, then what we're going to get to now is not the hard margin SVM solution, but actually the max L1 margin solution. Okay, so we get a different inductive bias, and you'd probably call these two things completely different learning algorithms with very different learning properties, very different generalization properties. Okay, and again, the only thing that distinguishes, sometimes these will generalize well, sometimes this will generalize well. The only thing that distinguishes between them is not your model, just linear models, or your objective function, just logistic regression, the only thing that distinguishes between them is the optimization algorithm that you used. Okay? And maybe a more interesting example is from metrics factorization. So if I solve something like a metrics completion problem, and I do gradient descent, so I'm going to solve a metrics completion problem with gradient descent just on the metrics. This doesn't make any sense. Instead, what I'm going to do is I'm going to write the metrics as u times v. And I'm doing gradient descent on u and v. Okay? But u and v still specifies all possible matrices. Okay? And now, if my optimization, I just changed my optimization algorithm, I'm going to do gradient descent on u and v. And I'm going to get to a zero error solution. I mean, you can always find a matrix that has zero error for a matrix completion problem, but it's not going to be just any solution. It's going to be the solution that minimizes the trace norm or the nuclear norm. And again, minimizing the nuclear norm is actually a very good inductive bias in many cases and can lead to learning. Okay, so to summarize the recap, did anybody understand anything? Okay, good. Okay, so to summarize the recap, what we talked about is here is that how the geometry of the optimization algorithm changes things. I can go from, if I go from gradient descent to coordinate descent, I can really change what I'm getting to. Okay? But here we started seeing something different because we're still talking about gradient descent, but what we change here is actually the parameterization. And that also really has an effect on the geometry, okay, of what's going on. So this was, again, from metrics completion. So I want to know two things here. One is the change of geometry. We got a really rich inductive bias, minimum nuclear norm, by changing the parameterization. And the second is it goes back, if you remember they talked about the oceans, I said that I'm optimizing, my model class is really all possible models. Then also here, my model class is all everything. In this case, all matrices, right? I'm solving a matrix completion problem, and my model class is all matrices. That's a really stupid model class for matrix completion. Right? That doesn't, just includes everything and doesn't give me any inductive bias. All the inductive bias is coming from the optimization through the choice of geometry. Another example in which we can see it, which maybe some of you have seen, and if not, I think maybe Surya will talk about tomorrow. Yes? Maybe, yeah? So another thing we're going back to these reruns, with TV reruns, they're sometimes out of order. So these talks are also a bit out of order. We switched, there's a last minute switch, so Surya's talk, which is tomorrow, should logically come before this one. So you should put this on your stack and pop it back tomorrow. Okay, so if we're looking at training a linear convolutional network. So what's a linear convolutional network? It's a neural net with convolutional layers, but with linear activations. Okay, so what's a neural net with linear activations? It's a really stupid object because at the end of the day, just parameterizes a linear mapping from input to output. So why do I have these convolutional layers? They shouldn't do anything. I'm just training a linear model. Okay? So this is just a complex overparameterization for linear models. And remember that if I do gradient descent on the linear model, what I'm going to get is something like max margin. And it turns out that if I do sort of with logistic loss, it turns out that if I do gradient descent on this strange parameterization, then suddenly something very rich comes out of it. What I get is I'm going to minimize, I'm going to get sparsity in the frequency domain. So with one convolutional layer, what I minimize is the L1 of the Fourier transform of my model, of my linear model. And with deeper layers, I'm going to minimize roughly implicitly minimize the bridge penalty, the LP bridge penalty. For sort of like with 10 layers, I'm going to minimize the 0.2 quasi-norm, or whatever you call it, for on the frequency domain. So with deeper and deeper convolutional networks, just by changing this parameterization, I'm really getting here very rich inductive bias. So again, we see the same phenomena. I'm optimizing over everything. So if my model class is everything, what is everything here? Everything here is all linear models. That's, we're living in a linear world. That's all we care about. The only thing I'm changing is the parameterization, and I'm parameterizing it in some strange way using convolutional linear networks, and I'm getting very rich inductive bias. I'm getting sparsity in the frequency domain. Okay, so far I'm talked to you that everything is matrices or everything is all linear models. We can also talk about everything being all functions, okay? At least all univariate functions. Okay? So now consider learning a univariate function using a single layer ReLU network. So now we're really talking, so with a single layer ReLU network with sufficiently large size, and think of it as infinite size, I can represent any function from R to R. Okay? Okay, so what happens if I actually train this network with gradient descent, or at least in this case, gradient descent with weight decay? It turns out that what happens now is that just by doing this reparameterization, I'm putting an inductive bias which corresponds to the integral of the absolute value of the second derivative of the function. So some kind of second order total variation or smoothness constraint. And again, this doesn't come, this integral of the absolute value of the second derivative, I did not specify it explicitly. All I said is I'm going to parameterize all possible functions using infinite width Rayleigh networks. Okay? By doing that and considering that parameterization, I'm implicitly inducing this extremely rich inductive bias. Okay? So the thesis I'm sort of trying to promote here is that really what happens in neural networks, it's not that I put in the slide at the beginning that, oh, the architecture is not important. It's not that the architecture is not important. The architecture is very important. The model class defined by the architecture is not important. The model class defined by architecture is all functions. That's not important. Okay? Why is the architecture important? Because I have my parameters here, and this is, again, relates very much to Leon's talk, and the optimization maybe puts a very simple inductive type of inductive bias on these parameters. Okay? Some kind of like simple spherical-ish inductive bias, but the choice of parameterization, the architecture specifies a choice of parameterization, which means a mapping from these parameters to the function space. And after all, what I care about is the function space, okay, whether it's linear functions or all functions. And what we saw is that by specific choices of parameterization, specific choices of architecture, what gets induced in the function space can be extremely rich and interesting inductive biases, like this second order total variation, or sparsity in a frequency domain, or trace norm. Okay, okay. So this is okay. So now let's try to see if we can get. I mean, if understand this maybe more generally, not in these concrete examples. So we can, in fact, do that. Let's focus at least on linear models. So models, okay, sorry, not focusing on linear, take it back. Okay, so let's try to understand that generally. So in order to do that, since I'm saying that everything here is about the parameterization architecture, we can think of this function capital F as the function that maps from our parameters to our function, to our model. Okay, so in other words, you can think of if I have I'm going to use little f to map from a model and inputs to the output of the model and those inputs, and capital F maps from W to the function implemented by that W. Okay? So for linear models, for example, I have that fwx is some linear function determined by W times x, and my model function is the mapping from W to that linear function. So for convnets, for example, it takes my weights and outputs the linear transformation given by that model. So what we can say is, at least for dehomogeneous functions models. So what's dehomogeneous functions? So dehomogeneous means that if I multiply all the weights by some constant, then the output gets multiplied by that constant to the power of d. So you should think of d as roughly the depth of the model. Right? So one homogeneous, just linear models. Two homogeneous things like matrix factorization or two-layer networks, and dehomogeneous and generalist things with depth d. Okay? So at least for homogeneous networks for any order, then in fact what we saw before is roughly correct. Okay? So we can say that the inductive bias in the parameter space is very, very simple. The inductive bias in the parameter space is just given by minimizing the Euclidean norm. So this is, if I this is the inductive bias of doing gradient descent on logistic regression with a dehomogeneous parameterization, is just given by minimum Euclidean norm in that parameter in the parameter space, and then the inductive bias induced into function space, okay, then is just simply given by mapping this inductive bias in parameter space to function space. So for each function, the kind of complexity cost of that function is the cheapest way to represent it, cheapest in terms of Euclidean norm in that parameterization. Okay, so this suggests that actually when I started by saying that, the importance of geometry, maybe it's not, maybe all this geometry of optimization, I don't really this emphasis on optimization algorithm is really unfounded, because maybe all this implicit regularization really all boils down to just L2 in parameter space plus the importance of the mapping. So this would be, I don't know, maybe good news and maybe bad news for us, because that means that the past 2 years of research of trying to understand this connection between optimization, the optimization algorithm, and inductive bias, maybe it all boils down just to mapping the Euclidean norm in the parameter space to what's going on in function space. And we did see this exactly happening both for metric structurization and for these linear convolutional networks and for these general homogeneous models. And so is this the case? So there's some evidence here that it is. There's also some evidence that what's going on is more complex. So one thing is, do these conditions, especially the homogeneity, actually hold? Is it really the many of the models we're looking at that succeed are not necessarily homogeneous? It's very possible that we know that there are more complex things are going on. More than that, there's some subtleties in going from, what we can guarantee here is only not really minimizing the parameters, the Euclidean norm of the parameters, but only converging to first-order stationary points here. And the transition between first-order stationary points in parameter space to even local optima in the function space is actually not at all direct. I mean, there are many first-order stationary points here that do not map to local minima in parameter space. And recently, there's some evidence that with squared loss, or our results are for the X loss, or the logistic loss, and there's some evidence from Sanjeev Arora's group that for the squared loss, this does not happen. Okay? So that for doing gradient descent on even homogeneous functions, particularly deep metric spectralizations, does not correspond to minimizing the Euclidean norm in parameter space. And this suggests that maybe also for the X plus, the connection does exist, but only at the asymptotic limit of the optimization where you optimized got extremely small error. And for any reasonable small error, some more interesting things are going on here. So this is one, wait, how much time do I have? I'm just about to, okay, I should start. 5 minutes? Oh, wow. Okay, I went through this a bit too slowly. Okay, so we'll soon get to the main meat here. Okay, so this suggests, that's fine. So this is also a very important point. So this, no, 7 minutes is fine. 8. Okay, so this suggests that, that really there's something more going on here. And then we'll soon, at the end of those 8 minutes, see maybe some more evidence that what's going on here is maybe more complex than just minimizing the norm in parameter space. But especially after Mahdi's talk, when I'm talking about the implicit regularization, where the optimization goes to, you might be thinking if all this boils down to just looking at in the kernel regime, so Mahdi's results, I guess, actually, where is Mahdi? He was here a second ago. I guess you didn't actually explicitly mention the, okay, so you tricked me. But there are many recent results that suggest that look at how study how neural networks operate in terms of the tangent kernel. Okay? And those results, by first reading them, kind of, again, is something that should make you doubt whether all this, we can actually get all these rich inductive biases. So let me just recap. So what do we mean when we talk about the kernel regime? So for any model, we can always locally look at a linear approximation of that model. Okay? So once I look at a linear approximation of a model, it's a linear model, and I can capture it with a kernel. Okay? And this is kind of the kernel that captures the local behavior, the tangent behavior around some initial model W. Okay? And there have been, and there's been some results that study neural networks just in that kernel regime, when this linear approximation actually captures what's going on, and show that actually you can get zero training error in the kernel regime, which suggests that you never leave the kernel regime. But if you never leave the kernel regime, all your training behaves as if it's a kernel. And then we know exactly what the inductive bias would be. It would just be the minimum kernel norm for squared loss, or max margin, hard margin SVM with that kernel in the case of logistic loss. But that view seems to kind of be very different from what we saw before, because what we saw before is all kinds of rich behaviors that cannot be captured by kernels. Okay? So in particular, if we focus even on, we've got rich behaviors that cannot be captured by kernels. So things like the trace norm or this second order total variations are things that are inherently not kernels. There's no kernel that would give you that inductive bias. So what's going on here? So it seems that what plays a crucial role is the scale of initialization. This was pointed out by Chizat and Bach in a recent paper that was mentioned already several times. So let's stick to these dehomogeneous models. And we'll look at a dehomogeneous model. We'll look at infinitesimal step size. We'll look at the behavior of gradient flow rather than gradient descent. And we'll initialize to the model with some scale alpha. Okay, so alpha is going to be the scale at which we initialize the model, and then we'll let it evolve. Okay? And what we're interested in is where will this gradient flow converge to? So it generally converge to a zero-error solution. We're not going to be concerned here about conditions for get zero error. Trust me that we'll always get zero training error. But the question is, which zero training error solution are we going to get to? Okay? And so, and the question is, will this behave like a kernel? Okay, like the flow that you get from the kernel. And what Chizat and Bach showed is, at least for squared loss, if I take this initialization to infinity for any model, once I take the initialization to infinity, at least if I can get zero error, then throughout the entire training, I will behave, the trajectory of training will behave like a kernel. The kernel, in other words, the way Mahdi discussed it, the tangent kernel is not going to change through training, which means that what I'm actually doing is just training a kernel model, and I get very kind of maybe boring inductive bias. What I get is just the minimum kernel norm. Okay? And so I can't do anything that I cannot do in kernels. Okay? But we saw before that we actually do get things that you cannot do in kernels. And something crucial that I glossed over before is, at least with squared loss, to get these rich behaviors, like for example, get the minimum trace norm solution, we have to get the initialization to zero. So it seems that the crucial thing here is, how do we initialize? When we initialize very large, we get a kernel behavior, and we get this really leverage the depth and get the rich behavior, we have to put the initialization to zero. Okay, so in order to understand this very exactly, we consider the simplest possible model which exhibits this kind of behavior. And this is, again, a linear model, but with a very strange parameterization. It's a linear model with a two homogeneous parameterization. So you can think of it as a simple two-layer neural network. Really, it's just a linear model, but each coefficient we parameterized by is a square of our parameters. And we include here actually two parameters for each coordinate. So each coordinate is given by the square root of the positive part minus the square of the negative part. And this is for two reasons. One, so that we can actually get all linear predictors. We can get both negative and positive coefficients. And the second is so that we can initialize in a way that has very large magnitude in parameter space, but is still zero initialization in function space. And, okay? So if we initialize all of these weights to some scaling of to alpha, to the same alpha, scaling alpha times all ones, then we can make alpha very large, but this corresponds to a linear predictor, which is just a zero predictor. Okay? And let's and what we're going to look at is, what inductive bias do we get? So initialize to alpha, and I'm going to look at beta alpha infinity is going to be the linear predictor that I get at the end of training. So it's going to be a zero training error predictor, but which zero training error predictor? So again, Chizat and Bach tell me that when alpha goes to infinity, I'm going to get the minimum of the kernel regime. You can work out the tangent kernel initialization here. It turns out to be just the scaling of the standard Euclidean norm. And so I get the minimum L2 norm solution. But as a special case of some results we saw before in matrix factorization, we know that if alpha goes to zero, we get a very different inductive bias. So what we get is the minimum L1 norm solution. So just changing the scale initialization gets us completely different inductive biases here. So it's the same model, and the only thing I change is scale initialization. Okay? Moreover, we can actually understand exactly this transition. So you can work out here analytically the inductive bias that you get for any finite initialization alpha. Okay? And this is given by this penalty. So again, you definitely get a zero error solution. You're always going to solve your linear system, and you're going to get a zero solution that minimizes this hyperentropy penalty with scale alpha. What this means is that I have a function q, which is given here explicitly, but don't look at this. I'm going to show you a plot very soon, scaled by alpha. So how does this function look like? I mean, it's very nice that I can write it analytically. What is important is this function looks like this. Okay? So around 0, it's quadratic. And away from 0, it's basically linear. Okay? So now let's look at the scale of initialization. Yes?
What happens to the square root when b is larger than 2?
What happens to the square root when b is larger than 2? That's an excellent question. Can be, yeah, b can, I'm sorry, what?
It's a complex number.
Branch of the square root do you take?
What? Sorry? That's a plus in here, right? No, yeah, sorry. Yeah, because it's a plus here also. It's a plus, sorry. Maybe it's a plus also here. No, sorry, that should be a plus. Sorry, that should be a plus. So it's always fine. Okay, so what? You're still not?
No, yeah, I'm satisfied.
Okay, I mean this is okay. So wait. No, it should be b. No, it's fine. It's a plus. This reminds me. It's fine. It's fine. It's a plus. Nothing special for b equals 2. Okay, it's just a plus. Okay, so what happens here is that when I initialize with alpha goes to infinity, that means I scale all my coefficients towards 0 just for the purpose of calculating this. And what's important is the behavior of this regularizer around here, and I have essentially an L2 regularizer. When I initialize with alpha goes to 0, okay, then what's happened is only behavior here, and I get L1 regularization. But any value in between, I'm going to get some interpolation of L1 and L2 regularization. Okay, so I get your interpolation of L1 and L2, and when you talk just about L1 and L2, maybe that doesn't seem very special. But remember that L1 versus L2 can make a huge difference in terms of generalization. So if what we're facing is a sparse problem, so we have a sparse linear regression problem. So I generated if the truth actually behaves according to a sparse model. If I'm at a large alpha, meaning that I'm effectively minimizing the L2 norm, I'm not going to get any learning. Okay, so this is here, and what I plotted here is actually this is the generalization or the population error of training. In order to learn, I need to initialize alpha to be very, very small. Okay? So in other words, what we're seeing here, this is the kernel regime over here. In the kernel regime, we're not going to get any learning, okay? Because the kernel here is not actually doesn't provide any useful inductive bias. To get good inductive bias, we want to get this rich inductive bias that leverages the depth of the network. We need to initialize with alpha that's small in order to behave more like an L1. Okay? And we see transition here from a small, the rich regime that takes advantage of the depth to the kernel regime. Now, we have to balance this with another consideration, which is when alpha is very, very small, it's very hard to optimize. Because remember that we're going to initialize at scale alpha. 0 is a saddle point. So we initialize to very, very small alpha. That means we're starting to optimize very close to a saddle point. Okay? So here it's easy to optimize. This is where all of Mahdi's results about kernel optimization live, and it tells us it's very easy to optimize very quickly, and we're going to get to a global minimum very well. So in terms of optimization, we want to be here. In terms of learning, we want to be here, but optimization becomes very, very hard. So which alpha are you going to choose? The alpha you're going to choose is going to be just at the edge of the rich regime. Okay, so the regime we want to be here is not actually fully the rich regime, but actually this transition between the rich regime and the kernel regime. Okay? Another way to see it is as follows. So let's look at the same sparse regression problem when you have more and more and more and more data. Okay? And which alpha do we want to use? We want to use the alpha that will make optimization the easiest. So we want to use the largest possible alpha that would still allow us to learn. Okay? If we're right on the information threshold, we really need to use a very, very small alpha in order to get the right inductive bias. And optimization will be very, very difficult. As we have more and more samples, we can very quickly allow ourselves to use a much larger alpha. And now over here, we can actually also do the optimization. I mean, this is just hand waving, but reasonably efficiently. Alpha is a reasonable value. We start away from the saddle point, and we can still optimize. Okay, I promised you a relationship to, okay, so I promised you a relationship for 0 minutes, fine, perfect. A relationship to explicit regularization, and you can ask whether we can actually understand all this just in terms of, again, minimizing L2 in the parameter space. So you can say, well, what does initialization correspond to? I say that roughly speaking, what I look at is distance from initialization. Also for least square problems, you don't actually minimize the Euclidean norm, you minimize the Euclidean distance to initialization. So let's define the linear regressor, which is here, or linear solution here, which is the minimum, the zero error solution, which is closest in Euclidean distance to the vector of all alphas. Okay? So this would be the direct regularization version of initializing to alpha and then doing gradient descent. And we can ask, are these two the same thing? So it turns out that also here we can write the solution as minimizing some implicit regularizer. This defines an implicit regularizer. And I can write down exactly what this implicit regularizer. And this implicit regularizer turns out to be the solution of this quartic equation. Okay, that's the exact quartic equation is not so important. What's important, what, you're going to check that it's correct? Maybe it's important to Andrea. Okay. What's important is, remember that before we had this transcendental function involving a hyperbolic sign. That's very different in solution to a quartic, which is just algebraic. Okay, so I can plot here both of them. In fact, they're very different. In particular, a solution to a quartic equation is just a rational function, which means that it goes, if I ask how quickly when alpha goes to 0 am I going to get L1, that's going to be polynomially fast. As opposed to this Q function, what I get from implicit regularization due optimization, because I have the hyperbolic sign there, then alpha has to be exponentially small in order to approximate the L1 norm. So there's a very fundamental difference here between the explicit regularization and the explicit regularization I get by saying I want to be close to initialization, and the implicit regularization I get by gradient descent. Okay. Okay, I have to finish here. I'm going to tell you that all these things carry over also to the metrics case, though maybe less rigorously. In the metrics case here also you can talk about the problem in the same way, talk about the kernel regime and the rich regime. The rich regime here is minimum trace norm, and the kernel regime here is really lazy. It just says complete the observed entries and don't touch anything else. Okay? And as you move between them, we can see also what happens. Maybe Surya is going to talk about that tomorrow. But let me just conclude here. And again, I think that the important thing I completely agree with some of the sentiments that Leon said before, that the important thing in understanding deep learning is really not the model class, but the optimization. Where does optimization get you? It's not enough for the optimization to be easy. We actually want optimization not to be too easy, so it also gets us to interesting rich models. Okay? In order to do that, we have to apparently understand both the optimization of the geometry of the optimization itself and the inductive bias of the optimization. It's not enough to just rely on explicit regularization. It seems to me that the main force actually at play is this implicit regularization of the optimization algorithm, not explicit regularization, and understand very carefully the parameterizations used and the role they play. Okay, thank you.